Welcome back. So let's talk about some of the evidence that helped to support this plate tectonic model that Alfred Wegener had kind of thought up, thinking, oh, the continents kind of, the shape looks like they match together. So what else is there? So that's what we're going to talk about. Firstly, is that a word? Where's the true edge of a continent? Where does our continent end? Well, I'll give you a hint. It's not at the shore. The true edge of the continent and continental crust typically extends out a little bit from where we see the shore of the ocean. That could be a few miles. It could be 100 plus miles. It just depends on some other geologic activity, ocean activity, etc. But the true edge of the continent extends all the way out to the end of the continental shelf, down to the continental rise. So this is the true edge of a continent, all the way out to the edge of the continental shelf. Now the continental shelf is still continental crust, but obviously due to ocean activity, water will tend to break down, weather, and erode rock, and kind of flatten it out a little bit. So at one point, the continent would have bulged all the way out to here, but over time, again, weathering and erosion, that's the breaking down of rocks and movement of that material due to wave motion, storm motion, for millions of years, kind of ground down the edge of the continent. So the continent still extends underneath the ocean for a little while, and that's the continental shelf. So that's the true edge of a continent. So if we're trying to figure out, whether or not continents fit together, well, let's not just look at where the shore is, where the beach is. We got to consider, all the way out to the edge of the continental shelf. That's the true edge of the continental crust itself. When doing that, and we kind of fit together South America and Africa, you can kind of see it fits together a lot better. So these lighter areas are areas of continental shelf. If it wasn't for those, the edge of South America, or the eastern coast of South America is here, the western coast of Africa is here, there's a big gap. But when you do consider the continental shelf, those pieces fit a little bit better together. So that's great evidence. That's kind of still working with Wegener's idea. What else? What else is there? Well, as we started to look at, again, for example, South America and Africa, we noticed that the ages of rocks on either side of the continent were the exact same age. They're right around the exact same age. Okay, that's interesting. And how that kind of matches up, how the ages of rocks kind of match up. Look at this, older than 550 million years. Just so happens that in South America, this little blip matches up with this area, about 550 million years old. So again, the ages of rocks started to match up. What else? Not only ages of rocks, but geologic formations. So we're looking at mountain ranges in North America, Africa, Europe, getting into Asia a little bit. Well, on their own, okay, but when you, again, recreate Pangaea, you can see how mountain ranges all kind of fit together. It's one long continuous mountain range, the Appalachian Mountains through North America, getting into some of the mountain ranges again in Northern Africa, through the United Kingdom, up into the Scandinavian countries, and into Greenland. So even geologic formations start to add up. Interesting. What else? What else could there be? Fossils. All right, fossils. So again, we're looking at fossil evidence in the rocks, and we're finding fossils on South America, we're finding fossils on Africa, India, Australia, Antarctica. We find all these fossils. A good example would be this fossil Glossopteris. It's a leaf from an ancient tree, and we found the same fossil leaves, in all of these different areas. Typically, you don't have that. The trees look different, in North America versus what they look like in Africa. Or heck, even think about the trees we have in Arizona versus if you've ever gone to Colorado, some of the trees we have there, or the trees in Pennsylvania. They're all different. So typically, different trees grow in different places. So the fact that the same tree grew in all of these different locations, even though now they're all separated by oceans, is kind of weird, but it makes much more sense. If you put it all together, wow, it kind of matches up. So it makes sense that the range of this ancient tree was actually pretty similar, again, once you stick all of these continents together. Plus, also weird to find fossils of leaves on Antarctica. Antarctica is a pretty cold and barren place. So therefore, if trees were once on Antarctica, then Antarctica, it wasn't where it is now. It had to be somewhere else that had the climate and the ability to have trees. Another great fossil is a Mesosaurus. Again, found on South America and Africa. On its own, whatever, but once you stick the continents together and you can see the range of this type of animal, the same range. And there's a number of different types of fossils in which we can kind of recreate this. One being the Lystrosaurus. More on this on the assignment in Unit 2. But that's the Lystrosaurus is a great piece of evidence, kind of a clincher in the theory of plate tectonics. Remember, theory, highest level of knowing. Testable, repeatable, never been proven false, widely accepted. And that's kind of an image, a little cartoon image of a Lystrosaurus. Oh, it's so cute. Look at it. It actually wasn't that big. It was like a little puppy dog. Look at that. Look at that. Look at this little big. That's so cute. As my daughter would say. It's so cute. You need more evidence to show that at one point the plates, the tectonic plates of Earth has kind of squished everything together. It kind of squished all the continents together. One weird one is glacial evidence. Looking for something called glacial striations. As large chunks of ice, glaciers, move and they slide, they do move and slide, they really scour and scrape the ground, the rock underneath them. Some glaciers can be miles thick, and as they move, they can cut through rock like a hot knife through butter, just very easily. Ice, big chunks of ice is actually very, very strong. So it can cut, polish, and scrape. And as it moves and scrapes the underlying rocks, millions of years, go by, the glacier melts. Well, what's left behind, we can see underneath where the glacier once was, these scratches, these striations. Now, we see a lot of these striations in some places, and even some places we wouldn't imagine. Australia, you don't really have glaciers there. It's pretty hot there. India, you don't really have glaciers there. It's pretty hot there. Africa, for the most part, it's pretty hot there. This portion of South America. Again, so in these places, it's weird that glaciers would be there, or these striations would be there caused by glaciers. Well, on their own, it looks kind of weird, but again, you put them together, oh my goodness, you can kind of see a map of how these glaciers kind of flowed outward away from what was then the North Pole. Kind of a side note, every once in a while, the North Pole and South Pole, magnetic North Pole and South Pole flip. So this is when the magnetic North Pole was actually at the bottom of the Earth, the South Pole. So what this is showing you is that all of these continents had to be somewhere, one, where it was cold enough to have glaciers, so they weren't where they are now, and then putting them together, you can see how, if we're looking at a centralized glacier flowing out in all directions, we can see how those striations, the directions of those striations, indicate that. Again, it makes much more sense once you put everything together. All right? So, the evidence of Pangaea, this supercontinent that once existed on Earth, we can find all these little pieces of evidence, like the shapes of the continents, the age of the rocks, geologic formations, these fossils and glacial striations. On their own, they don't make sense. When we recreate and put continents together, all of this starts to make sense. So what that's telling us is what the world looks like now, that's not what it looked like millions of years ago. So, if at one point the plates were together, but now they're not, that's telling us they move. Hence, the theory of plate tectonics. Theory, highest level of knowing. But what about now? So this is evidence that all of this stuff moved in the past, but what's missing? Well, it's proof of plate movement now. Well, that happened in the past. How do we know it's still happening? Maybe it's not happening anymore. Let's find some more proof. So, what we can look at currently is the seafloor splits and moves apart along something called a mid-ocean ridge. This is a divergent boundary. New oceanic crust forms. As it does, this crustal material gets pushed away from the center mid-ocean ridge. So, as the rocks get further away from this mid-ocean ridge, the rocks get older and older and older, or younger as you get closer. So, if in the middle we have the youngest rocks, and at the edges, as we get further and further away from this split in this oceanic crust, the rocks are getting older and older and older, this material is getting pushed away. So what it's telling us is that at this area, the crust is splitting and moving things apart. We can also see it, again, going back to that North Pole, South Pole flipping. We can look at some, and this is getting a little technical, but looking at the polarity in rocks, and we can look at how the magnetic field at the time influenced different magnetism within the rocks. It gets a little complicated, but we can see the poles flipping. That's how we know the North and South poles flip every so often. So you can see, plus minus, plus minus. This is the magnetic fields of the Earth going different directions. So once we discovered this, and this happened in the mid-1900s, as we're mapping the seafloor in an effort to create a map under ocean floor map for submarines, so they know where to navigate, they came across this, and more in a little fun video in the next section. But actually in this section. No, the next section. But in any case, so this was a great piece. So we see this happening now. We see the seafloor spreading and oceanic crust, new oceanic crust being created. So you're creating brand new rock here, and that material getting pushed out. So we have a mechanism of movement, and we see this happening now. So this is proof of movement going on right now, seafloor spreading. And then let's use some additional technology, GPS. We have it in our phones, we have it in our watches, we have it in almost everything. It's a great tool. Well, GPS stands for the Global Positioning System. We use satellites to just take a look at Earth and at any point and see, we can trace how fast something is moving. Well, we can do that with the continents. So we can look at points on the Earth itself. For instance, here's North America, the United States. We can see that the vast majority of the United States, which is on the North American plate, is kind of moving down and to the left, kind of in the southwest direction. But you can see portions of California, which is on the Pacific plate, oddly enough, kind of moving up and to the left, so kind of to the northwest. So North America, parts of North America are moving in different directions. But anyway, this is a valuable tool. Again, we can use it to track plate motions as the ground moves. Points on the same plate all move in the same general direction. So we have evidence of Pangaea in the past by looking at all these different things. So we know plates moved in the past, and we also know, guess what, plates are moving now. We can see it with seafloor spreading, with GPS. All right. Uniformitarianism, the past is the key to the present. So we know plates move in the past, they're moving now, and we have evidence of that. So we can use this evidence and proof now to recreate how the surface of Earth changed and what it looked like all the way back many billions of years. So Pangaea wasn't the only supercontinent that was ever created. If we go back and look at all this same evidence and kind of put the tape in reverse, we see the motion of the plates now. Well, let's just put it in reverse and kind of keep going back. We can actually recreate quite a few numbers of supercontinents. Pangaea just happened to be the last supercontinent. But going back even further in time, Pannotia, Rodinia, Columbia, Kenorland, and Ur. So all of these can be recreated with that same information. Rocks, formations, fossils. We can match it all up. So we'll pause here. When we come back, we'll briefly talk about these different supercontinents, and also I'll see you back here in just a minute.